this is Craig Resnick coming to you from the ARC Advisory Group. With me today, I have two special guests. I have Oliver Brunke, who's the Product Management Team Leader, and Udo de Vries, Growth and Strategy Leader, and both come from a company called Waygate Technologies, which is a Baker Hughes business. So welcome, Oliver, and welcome, Udo.
Thank you, Craig.
Thank you.
Thank you so much for being here today. And, one of the things I want to start off with is, you guys talk a lot about computer tomography, lithium battery cell inspection. What are the advantages of computer tomography in lithium ion battery cell inspection? So if one of you could answer that, that'd be great.
Sure, Craig. So maybe I start with a little background on what computer tomography is, and we talk about X-ray industrial computer tomography, which is similar to what most of us are familiar kind of with, which is in many hospitals around the world. So technology which is based on an X-ray source and a detector. And what you do, you image the part, comparison to a standard radiograph, where you just take one X-ray image and then you look at this two-dimensional image and try to read it and interpret it. You'll take many X-ray images from different angles, if you will. And in medical CT, you spin your source and detector arrangement around the patient, the human body. And in that way, you get the image. In industrial CT, you typically do it the other way around. So you have a static X-ray source and a static detector, and you spin your component, in this case, the battery cell, for instance. And then by this, you can create a three-dimensional representation of the component of the battery cell. And the coolest thing about this industrial CT is it allows you to go into the internal structure of this particular component in a pretty detailed way. So we can image components down to even sub-micrometer level. So with our technologies, we can cover a resolution range of a little bit less than 1 micrometer, which is really small. That's less than 20th of the diameter of human hair. And that we can really analyze the microstructure of components. That's one extreme. We also can image parts at a less high resolution but fast, and then we can image components in a very short amount of time. Let's say maybe 30 seconds or so, and inspect a lot of parts and understand the quality. So how is that related to lithium ion battery cells? Lithium ion battery cells obviously are very interesting component for many industries. They drive our cell phones, our portable devices. They more and more are the energy source for vehicles, for electric vehicles. So the next generation of drivetrains, which is currently rising a lot, is battery driven, lithium ion battery driven, and also they are used obviously in other energy storage situations for boats, for houses. So lithium ion batteries is a very fast growing application. And one important aspect of that is to ensure the quality of these components, both for ensuring the safety of the battery cell and the respective part or component where it's used in, but also, of course, for the manufacturers of the cells or the users of the cells. You want to minimize the cost of quality. And with X-ray CT, you can understand the structure and the dimension and the defects of these components, potential defects, non-destructively. Yeah? So without the need of cutting the cell mechanically open, you can look inside. And you can look inside, as I mentioned, on a pretty high detail level. And with this, you can, with this method that allows you to understand the nature of the defect, the origin of the defect, and also then understand how this defect can be avoided. And by that, you can improve the performance of your component, in this case, the battery system, the battery cell, but also you can reduce the defect rate. So that translates to reduction of scrap rate, and then of course it translates to cost of quality reduction. And gives you therefore a lot of opportunity to improve your quality, and then at the end of the day also improve reliability of your battery cell. So that's maybe in a nutshell an answer to the advantages of X-ray CT for lithium-ion battery cell inspection. Udi, do you want to add something to that?
Maybe the only thing is a lithium-ion battery cell is built out of many different components, and in the assembly process of these many different components, anodes, cathodes, separators, a housing, connectors, screws, all kinds of things. A lot of things can go wrong. So with computer tomography, you have the chance to inspect each and everything, as Oliver described, and you can really pinpoint it down. Whereas when you cut it open, you lose a lot of the evidence of what's in there, as you do it in all other destructive methods.
That's really fascinating, Udo. One of the questions I would have is that, like, in which phases of product life cycle can computer tomography be applied to batteries?
Good question, Craig. It's really cradle to grave. So from the very early stages of designing a battery cell for a certain application, really to end of life batteries and inspecting the ones which are in service or post-mortem once the cell has died. What does it mean is that when let's take a car, you have a car, you want a sports car, and they want a battery which is super, which allows for fast decharge in order to propel your four engines, that you can go from 0 to 100 miles in 2 seconds. I make something up here, but so the battery needs to be very strong. So they design a specific cell in terms of size, but also electrical capability for this purpose. And this is done usually as prototype cells because they test around with certain dimensions, chemistries, etc. And already in this phase, it's very important to verify whether the concept is fitting. And that's where we come into play. Next is then when this cell is going to the pre-series production, so beta series, then you want to look, can I really mass produce this kind of cell at the appropriate quality? Are all the areas that I want to inspect okay? Or is there anything which pops up in the manufacturing process which is, let's say, difficult or which produces problems later? In mass production, obviously, you want to have everything stable, everything in the same quality, because once these cells are integrated into your sports car, you don't want your sports cars die, especially not when you're in the middle of nowhere, but also you don't want any risks coming out of this battery. And in the case, now we come to the in-life inspection, in case there's a problem that the capacity of your battery goes down, with CT you can look into the modules that are in under your car to verify there's any mechanical issue. So, and after one of these batteries has died, obviously you can also do a more comprehensive analysis to find out whether there's anything to learn, which you can use again at the beginning of your life cycle to improve for the next generation of batteries.
Is there any, I'm thinking in terms of like which batteries and battery systems can be inspected. Is there any limitations to that?
We are talking here about really lithium-ion batteries. And for lithium-ion batteries, the ones which we have these days in phones, computers, as Oliver pointed out, you find them in aircraft and in cars. There's no limitation on that. So what you find is in your household devices, you have cylindrical cells, which look like we all imagine batteries. These are very easily to inspect. And then you have so-called pouch cells, which look a bit like like a pouch where you have then anode and cathode in, and which are then sealed closely with a vacuum. And then you have canned batteries, which are so-called prismatic cells, and these are a bit like aluminum housings where you have then your anode and cathode in a roll in there. And these are the three predominant ones, and these are very easy to be inspected. The more interesting piece is, and that's where we play more a role, is that these, especially the pouch cells and the prismatic cells, are integrated into so-called battery modules, which means instead of connecting thousands of cells under your car, for instance, you build building blocks, a bit like Lego bricks, and these have then in themselves maybe 50 cells. But they are a part which is maybe 50 times 300 millimeters or bigger. And these can be then moved around, and usually these are sealed. So once they are sealed, you cannot look inside and find out whether everything is okay. So that's where we come into play. And the last bit is then everything which is under your car is in the end a battery pack, a lot of modules together. And we want to also help the industry here. And we have now a tool which is then a so-called high energy CT, where you can put a complete battery pack as a whole in and inspect it.
You know, is there another question I had is that in which customer locations is computer tomography applied to batteries?
So, I mean, Craig, maybe going back to the two previous questions, and I can try to answer this in relation. So, when we look at the product life cycle, what Udo described, so from cradle to grave, and when I go a little bit into the cradle part, so when you design batteries, you are also really looking into this what is called electrode design of cathode and anode. Typically, it's a slurry which is created, and you want to understand the composition of when this is dried out and put on the aluminum and copper tray foils which then form the so-called electrode stack. You want to analyze the grain structure of this slurry and understand is there inhomogeneities there. So in that would be a location for a typical R&D lab where you analyze tiny bits of this electrode and look really into the microstructure of this and understand what grain sizes do you have? Do you have inhomogeneities in there? Do you find foreign material on a micro level in there? To understand is my mixture, is my compound in the way I want it to be. So that would be an R&D center, and we have several installations globally, both from a public R&D perspective in research center, which are funded by governments, by research associations all over the world. That's where we find a lot of installations. So in the research area. Secondly, we have the quote-unquote traditional quality labs, so where you do your analysis of prototypes, where you do analysis of the ongoing manufacturing offline, and you also analyze post-mortem field returns. So, for instance, when a battery cell or system failed, you want to understand what was driving that. This battery cell is swollen. I'd like to look inside and see what is the root cause for this. And here we have, as I said, quality laboratories, which have a lot of different tools to use, and in many quality laboratories today in battery OEMs, but also in the users of batteries, you'll find a CT, a computer tomography system to do that analysis. And then, of course, the last but not the least, and a very fast-growing area is the production process control. So this is where we are looking into close to the factory or manufacturing line inspection up to full inline 100% inspection, where each and every battery cell is inspected by some sort of X-ray machine, and ideally with computer tomography, where you can then find several different defect types with one method and help to control the process, and also help to keep the scrap rate low. So that would be the locations you
there's one addition, Oliver. You also have it as a tool for incoming goods inspection. So meaning that most batteries are produced remotely. So batteries used in the US are sometimes produced in Asia and in China. Batteries produced in Europe at times come out of the US, etc. And in order to verify whether the quality is exactly as they want to, once they open the crates, they sometimes in the manufacturing plants where they integrate only the batteries into the end product, they want to scan the batteries to make spot checks, whether they are really according to what they've ordered. And also it's much easier with these images to compare against what was the, let's say, the wished for result, how the battery should look like, and also with the discussion with the supplier to compare the images and discuss over the continents.
Probably the last question I would have is, what kind of failures can computer tomography detect for lithium-ion batteries?
So we touched on this already a little bit in the previous answer. So I'd like to give a little broader overview on what we can do, because one major advantage of computer tomography is that we have a pretty broad application spectrum. So we can see a lot of different defects, if you will, or features of the component we inspect. Because we have a full three-dimensional representation of the inspected component. And for battery cells and battery systems, we would start on the electrode structure, as I mentioned already. Here we are looking at the inclusion of material. We have foreign material from different parts of that mixing process of the slurries you need for the electrodes. You have probably dust and abrasion of other materials from that manufacturing process of that electrodes. So that would be the electrode structure. Secondly, we have then the creation of the electrode stack. And here a lot of things can go wrong because we need pretty high precision on a relatively delicate part. So we have very thin metal foil, so just a few micrometers, and then on top on each of these foils you have a little bit thicker layer of active electrode material, and then you stack maybe 20, 30, 40 of these in alternating way on top of each other, and then you have to have a very precise stacking of these cathode anode arrangement. This is important because you need to make sure that you're not creating shortcuts, which in the worst case could lead into a thermal runaway event, which is a burn up of the battery, which you really need to avoid. Or in the other scenario, you just lose capacity of the battery. And both, obviously, the first part you really want to avoid, but also the second is waste. Yeah. So both you want to avoid. And in order to do that, you can measure a certain characteristic of this cathode anode stack, which the expert call the so-called overhang. So that's in easy word the distance between the different electrodes. So the distance between the cathode and the anode. And if this distance is too short, you have a problem. And if your distance is too long, you also have a problem. And so with CT, you can measure that distance in a very reliable way and try to avoid this defect. So that would be this one typical defect for stacking of this electrode cathode. Now you have a pre-assembled cell. Now this stack can move, as Udo mentioned, will be moved into the pouch or the casing. Here you can fill it with electrolyte. Here you want to understand, do you have the right distribution of the electrolyte as expected? Do you have gas bubbles which you want to avoid? So that would be something you can inspect as well with X-ray CT. And then the other big area is you can analyze the overall assembly of that cell. Should it, for instance, when you have a case, do you have the right welding? Is the dimension of the housing correct? And other mechanical deviations which can occur due to the assembly process you can inspect. So that would be in a nutshell the summary of defects or process deviation you can inspect with X-ray CT.
Well, it's really amazing that we have this technology, because there's certainly probably no one that does not depend on the performance of the lithium-ion batteries every day, even if it's just even part of your mobile phone use. So really, Oliver Brunke, product management team leader, and Udo de Vries, growth and strategy leader from Waygate Technologies, a Baker Hughes business. Thank you so much for being here today. It was an absolute pleasure.
Thank you.
Thank you.
And this is Craig Resnick coming to you from the ARC Advisory Group. Thank you so much for listening. Have a great day.